Hey, you know, when I log into Zoom, it usually shows me the meetings that I have every day, and this one was not listed there. Did I do something wrong when I set up the schedule of this class? Did you guys have any unusual experience logging into this class just now?
Nope, everything was pretty normal.
Okay, I don't know what I did. Maybe you know, they trained me as, no, they never trained me. I got experience as a teacher, and I know I've learned a lot about how to deal with students and how to make ideas as clear as I can do. And all of that's fine. The part I never really got was all the technology. It keeps changing on me. I think that's a sign of old age. I can't keep up.
Sorry, Professor, when I logged in today, I noticed all of my Canvas classes had come to the same page, even though, or even the ones I took before.
You talking about on Canvas?
Yeah.
Yeah, that happened to me too. I just thought it was some weird bug, so I'm just like, it's probably nothing.
Say again, what happened?
Like all the previous courses I've taken also came to the active courses page on Canvas.
You mean courses from previous semesters?
Yeah, like from 1, 2, 3 semesters ago. And it's just random ones for me too. It's not all of them, it's just random picked courses.
I've actually noticed that as well.
Well, I mean, it's possible, you know, they keep monkeying around with these things, trying to make them more secure or whatever. Every time they do that, it makes it worse. I mean, I totally remember one time I clicked yes to, do you want to upgrade your phone's operating system? And it bricked my phone, and then it cost me a couple $100 to get a new phone.
Someone got a virus.
No, it was, I don't know what it was. Anyway, it was time for a new phone anyway. All right, so let's just plow ahead here. Let me tell you, I gave you guys an exam that was due on Friday, and it seemed like most of you were able to get everything done, including the new part of scanning some free response questions. It looks to me like everyone's scanned answers came through all right. There were a couple that I'm not quite sure if students meant to only submit one answer or whatever. I am in the process of grading all of them. I had 200 and some odd to grade over the weekend, and it's down to less than 100 left. So I hope to have them done. If not tonight, I'll have them done tomorrow. So that will be the free response part. You'll get back a score up to 28 and some comments if I see something that I can correct on your paper. You should already have your score on the quest portion of it. Students have alerted me to the fact that apparently you haven't been told which ones you got right or wrong. That doesn't make any sense. So I'm going to talk to the quest people to see if we can get that kind of information to you. So I want to do two things. I want to talk about the test, but on two levels. One is I'm going to ask you in a minute about the content of the questions. So if there was anything specifically about the free response, but we can talk about the quest ones as well. I just want to make sure, obviously as your teacher, I want to make sure that you understand that material. But before we get to that, can you talk to me about your experience kind of technologically and so on? How did it work for you to be taking the quest exam? How did it work for you to be scanning in your things to Canvas? What was your experience? Did you have difficulties, anything that you want me to change by the time we get to the final exam? Because I guess I was going to make the final exam be just like this one.
The quest was beautiful.
Sorry, what?
The quest version was beautiful.
The quest was beautiful. Okay, I'll be sure to let the quest people know that you liked it. I selected the questions. I must have made it a little easier than some of my other quest exams, because as far as the quest portion goes, I saw there was a whole bunch of people that actually had perfect scores. And I think by and large, the rest of the class, even if you missed some, I didn't have very many people that missed a lot. So it's good for you guys and maybe good for me for choosing the right question. Yeah, so everything with the scanning was okay? I guess you made it work somehow.
Yeah, it works fine.
Okay. And I got to say, from my end, it seems to work pretty well. Also, I do appreciate you guys starting each question on a separate piece of paper. They use this thing called Speed Grader that lets me make comments and stuff right on the PDF, so that's good. I might, in the final, it might be even easier if I can get you guys to load up each question separately. I'll have it look like 3 assignments instead of just 1. But we'll see how that goes. It would be, some of you, it's a little hard to read your scan. It came out kind of faint. So if you could make sure you use a nice dark ink. I know you guys have trouble reading what I write sometimes on these Zoom sessions. And it's the same when I try to read what you scan. Occasionally it didn't work out too well. All right, let's talk about the math content then. Did you guys have any questions or comments about, well, for the free response ones, I made up an answer key and I just put it up this morning. I sent you guys an email. There's also a link to it. If you go to the course syllabus on the math department web pages, I don't know if you noticed, but near the top sort of, there's a bunch in boldface that's just about midterm 2, and I made a link to the answer key now. As a part of that boldface section, or right after that boldface section. But apart from looking at the answer key, is there anything that you need to talk to me about for those free response questions? Or the questions, I guess. No? Everyone's happy?
I was actually about to ask, will we have another homework assignment after this midterm?
Oh, yes, thank you for asking. Yes, we have 2 weeks left. So this week and next week are our regular classes. And we're short a week, but I'm going to try to get as much as we can of what would ordinarily be in the syllabus into these next 2 weeks. So I'll make, I guess, just one more homework set, and it will be due, I guess, on the last day of classes or something. I'm not sure if anybody cares with all the schedules messed up this semester, but I'm not ordinarily supposed to have anything come due during those no class days, you know, between the classes and the final exam. So I'm not sure if that means the last possible due date would be Friday, May 8th or Sunday, May 10th. But yeah, that'll be one last homework set, and it'll cover chapter 8 and this last section or 2 of chapter 7. Listen, as Quest gives me statistics on how well you guys did on each one of the questions that I gave you on the exam, and it seemed like most of you understood all the material. I mean, well, I had pretty high average scores on every one of those questions, except maybe the one about line integrals. That was still okay, but it was a little lower than the others. Of course, that was the newest material. So now maybe it's worth spending a little bit of time talking about the line integrals and using that to launch into the material on surface integrals with a vector field. So if you don't have any other questions on the other material that we've done up through now, I guess that's where I would launch into the actual mathematics for today. Is that okay? You guys good with that? 10 minutes in.
Yeah, let's go.
Let's go. All right, so let me spin the camera around here for you. And I have to go up this way. I'll figure this out by the end of the semester, how to make this work. Okay. So at one point, I made a set of topics in parallel lines. And so we were talking about the path integrals. And that's where I give you this real valued function, little f, and I give you a curve, and I ask you to compute the integral with respect to arc length. So you're chopping things up, multiplying lengths of the pieces times values of the function. And it's important under that circumstance that the values of the function just be numbers. I have to have a function that spits out a number at each point in space. So you'll be multiplying a number times a length, which is another number, and you add all those numbers together over all the sections of the curve. All right, so we were spending time doing that. That sort of required that we first had some preliminaries on parameterizing curves. And well, that's a tricky topic, but we did that actually a lot. We did that earlier in the semester. And then after we had talked about doing path integrals, we introduced this variant called line integrals. And the ingredients on a line integral are also a curve. You still had to have some sort of a curve, but you had to start off not with a real valued function defined on space, but a vector valued function defined on space. So this would be a function that was defined on R3, but it spat out vectors in R3. Oh, I'm sorry, that's too, it's getting kind of faded, isn't it? So the notation for this would be a little bit different. We tend to put a dot product, and we'd make it clear in boldface or with arrows or something that those are supposed to be vectors. And well, we said quite a few things about this over the last few days. So I tried to explain why you would care about such a thing. And all of the applications that I have come from physics or engineering. The most natural one by far is to say where this F might represent a force field, which is, so force is a vector. It has both a magnitude and a direction. And we're somehow only counting the contribution of that force in our direction of motion as we move along the curve. If you think about a vector as having components, then in particular you can talk about the component that points along the curve, and then there would be other components that are perpendicular to the curve. Those are supposed to be three perpendicular little vectors at each point on the curve. And we're just computing the portion, the component of the vector field that's in our direction, because that would represent work or something. So that was the concept behind the line integrals. We also spent some time talking about the notation, and then we spent some time talking about the theorems, really just one theorem. But I did have to spend a lot of time talking about the computation of line integrals, and that meant relating these to those. And I'll remind you of how we made that work again in a minute. But I want to recreate the rest of the diagram that I had up on that day, I don't know, a couple of weeks ago. Because all of these are topics that have to do with curves. This is kind of like the focus. This was the preparatory material, and this became an application. Okay, now for surfaces, we do something very similar. You have a surface integral. Try to get this a little less glaring. So a surface integral also begins with a real valued function defined on space. At each point in space, you get a single number. But instead of a curve, obviously, you're given a surface, a patch of surface that floats in space. And then the general idea of what you're trying to do is you have to chop this up and you multiply the area of each piece times the value of the function. Again, that's a real number, so you have numbers times areas, which are numbers. Numbers, 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 you add them up and you get a number. We had
I have a quick question.
Certainly, go ahead.
What does that word say above integral? I can't read that.
That's surface.
Surface.
Yeah, these are surface integrals, and they are, surface integrals are to surfaces in the same relationship that path integrals are to paths. In both cases, we understand what they mean. It's chopping up and multiplying. The only difference, of course, is you use lengths here and areas there, but the general idea of chopping up and so on is the same. And so similar also would be the method of computation. Every computation of a path integral begins with a parameterization of your path, of your curve. And likewise, in order to compute a surface integral, you have to begin by parameterizing the surface. And so we had your book actually devotes a whole separate section of chapter 7 to this concept of how to parameterize a surfaces. Right, so those two ideas are somehow in parallel. Of course, it's harder to do surfaces than curves just because there's an extra dimension. Some of you took longer to get used to the very idea of what it meant to parameterize a surface, because here the parameter could be called time, and here they're just two arbitrary parameters, u and v. But once you get used to parameterizing a surface, then you have a means of computing the surface integrals. And you still have an idea of what they might represent, depending on what kind of scalar valued function little f is. We talked about things like density. Here, this would be a linear density, and these would be what would be called a laminar density. It's like grams per square centimeter now. All right, but to complete this diagram, it feels like we need to have something that's parallel to this line of thinking. So we decided that we would get certain kinds of path integrals in a context where we started with a vector field. And I can do the same thing for surfaces. So in a previous diagram, I said not now for filling in this last box. Well, guess what? Now is now. All right, so let's talk about the specifics of this little diagram in here. So what we previously had was you understood how you would both interpret and compute a path integral. And as I say, that comes from the parameterization. Now, what happens when you have a vector field? What does it mean? Why would we even be interested in somehow integrating a vector field? What would that mean? And the answer to that question is not really mathematical so much as it's a scientific explanation. From the physicists and the engineers, we learn that given a vector field, so that would be either a function that takes every point in the plane and gives you a vector that points in that plane, or a similar thing in three-dimensional space. At each point in three-dimensional space, you get a three-dimensional vector. What we would do is we would let the function, the scalar valued function little f that shows up in this spot, we let that be the dot product of capital F with a unit vector u. And I'll put little arrows today just to emphasize that these are vectors. This would be the magnitude of f, but reduced by a factor of cosine of theta, where theta is the angle between the direction we're moving on the curve. So here's my unit vector u, and if the force is directed in that direction, then this would be the angle of theta. And for whatever reason, we might need to reduce the size of capital F by this cosine to get a single number, which is then multiplied by the length of a single arc. So then we could start to play the same game that we were doing up here. We could compute a path integral with this function little f. By far the easiest example to illustrate is where capital F is a force field, a vector field of forces, and you've been given a path, and as you walk along the path, the amount of work that you have to do is precisely this force. This little f. You take the size of the force, but you reduce it depending on how much of that force is blowing in your direction. Obviously, if the force is perpendicular to your path, you're not actually doing any work when you cross the force field. So the science, the physicists and so on, they're the ones who tell us that this is something they might want to compute. Here is a now scalar valued function. This is always a single real number, not a vector. It's a scalar valued function that they want to keep multiplying by lengths and adding up. And so now it feels like we want to compute a path integral. And so, well, we do that. We compute this little f, the integral of this little f over this path, only we change the notation to say where the little f came from. This isn't really anything but a notation change. We use notations like this, and I talked about some other ones like f1 times dx plus f2 times dy, whatever. The notation is supposed to be suggestive, but it just is intended that you compute this path integral, which is a number. You know how to compute it. You parameterize the path and yada, yada, yada. Along the way, a couple of other things develop. First of all, we discovered that there was a certain amount of magic that happens after you choose a parameterization for your curve. You think that you might have to get this unit vector by taking, let's say, your velocity vector, which at least points in the right direction, but it doesn't have the right magnitude to be a unit vector. So you need to take the velocity vector divided by the speed. And that looks complicated enough, but you know that as you compute a path integral, you have to multiply by the phi prime of t thing, which is also a speed. And then you realize that some magic happens. Those two references to the speed cancel. And so you are able to actually compute this line integral a little faster than the path integrals. You compute them by taking the vector field at each point in your curve, and you simply dot that with your velocity vector. And that becomes the thing that you integrate with respect to time, from your parameter of the curve, and you go from your minimum to maximum values. Right? So this is a cool thing that seems to happen by magic. It gives us a way to compute the line integrals at least as quickly as we can do for the path integrals. Now, you better ask me about this stuff if you're not clear, because I want to recreate that now in parallel, but do it for surfaces. Anything you need to ask for clarification here? All right.
Wait, you just said that the phi prime cancels out as like the speed though, didn't you?
Not the phi prime, the magnitude of the phi prime. So let me do that a little more carefully. Thank you for asking, actually. I said up here I needed to take a unit vector that pointed along the curve. So typically the way you get that unit vector is you take your parameterization that tells you your position, compute its derivative, which gives you your velocity. You know your velocity vector points in the right direction, but it doesn't have the right magnitude. It's not usually a unit vector. It's got a magnitude, and so you have to divide by the magnitude. Now you have a unit vector that you can stick into that spot. Okay, well, cool. But then look how terrible your formula is going to be as you go to compute this path integral. You're going to have to compute this by, well, you can use exactly the parameterization that you were using to get your velocity, but you'll have to take the function f and compose it with the phi. You substitute away all the x's and y's and z's that are in the definition of f, so that everything now just refers to time. And then you know you have to put in the fudge factor, and then integrate that with respect to time, and you integrate over your interval from the first t to the last t. But if little f was defined in terms of a dot product of capital F with the unit vector, I'll just replace this by all those symbols, leaving this behind because that was part of how you compute a path integral. Then when I write in what I'm going to use for you, check out what happens. You have f composed with phi dotted with phi prime of t divided by phi prime of t. So all of that much is just a rewriting of what it means to compute little f at the points on the curve. The values of little f are these dot products. And then the definition of how you compute any path integral says now you have to multiply by this differential. There's the fudge factor and the new differential. So I still have to put that in there. And here's the cancellation, the thing that I call the magic. So the two references to the speed are gone. The reference to the velocity, that remains. So in fact, all you're doing is what I set up here. What you're going to integrate with respect to t involves both the vector field itself, that has to be expressed in terms of your parameter t, instead of being referring to x, y, and z. But that's the vector field, the force field, say. And then you take the dot product with your tangent vector, whichever tangent vector applies to your situation as you use your parameterization. Everyone would agree on the direction of the tangent vector, but they would disagree on the magnitude of this tangent vector. Some people would be going faster or slower as they parameterize the curve. Turns out it doesn't matter because the two references to the speed have canceled. So cool, right? This is I called it magic, and it does mean that you can compute your line integrals a little more swiftly. All right, so that's what we said on the line integrals. So now let's introduce the surface integrals. So that'll be all done kind of in parallel to this. So can I keep that page parallel? I don't know. So let's see, before we discussed what a path integral is. Now similarly, we already understand what a surface integral is. You again have to have a real valued function defined on three-dimensional space. At each point in space you get a number, but you'll multiply the numbers, the values of this function at different points on a surface instead of on a curve. That's fine. And you'll multiply those numbers by the area of a chunk of the surface instead of the length of a chunk of a curve. So conceptually, it's all very similar. Practically speaking, it's only harder because it's harder to parameterize a surface than a curve. But now come the physicists, and they again are attacking us with vector fields. Since this is a surface floating in three-dimensional space, I guess I'll go right to this instance of what happens when you have a vector field in three-dimensional space. So you need to imagine some sort of three-dimensional array of arrows. And this can occur in a lot of different ways. One way I like to think of is, suppose that you have a visualization of a stream bed, and water is flowing as it enters and leaves the stream. Basically, it flows downhill, downhill. But you know, there can be little eddies that make it twist in places, or if there's someplace where the water gets warm, then you know the water will flow upwards. So anyway, there's little arrows, okay? That's a vector field in three-dimensional space. And now if you're also given a surface that's floating in three-dimensional space, somewhere in the river, I don't know, what might you as a scientific person want to know? I, as a mathematician, might imagine all kinds of goofy ways that I could combine a surface and a vector field. But the one that makes sense from an engineering point of view or a physicist's point of view is to look at the contributions of this flow as they pass this little patch of surface. So you could imagine, for example, that the surface represents like a mesh opening that stretches across. That means a mesh surface that goes across the opening of some kind of a drain pipe. So somebody wants to extract water out of the stream. Maybe this is the City of Austin water supply, and you'd like to know something about how much water comes through the hole, and that depends, of course, on how much water is flowing past in the first place, but it also depends on how this opening is situated. I mean, if you're expecting water to just jump into the pipe and you've made you made the opening just be flat, well, no water is going to flow in there, right? I mean, the water, unless the water is flowing upwards, it won't get into the pipe. So there's something about the orientation, the positioning of this surface that's going to matter, as well as the flow of water itself. You might also want to think about that surface there as being a net, and you have fish that are swimming in the water, and you're wondering about how many fish you're going to catch. Well, you know, you're going to get a lot of fish if you string your net over here at the end like that, whereas if you strung your net horizontally in the flow of the water, all the fish will just swim right past. So, you know, there's no dinner for you tonight. So, the long and short of this is that if you have a vector field and you have a patch of surface, there are sort of physically reasonable applications where it might make sense to take the portion of this vector field. You need to know something about how big it is, how strong it is, but you need to take that quantity and reduce it by some measure of an angle at each place. The angle here that I would worry about would be the angle between the flow and, I'll draw this vector here that's perpendicular to the surface. The issue here is that if this is your fishing net in the middle of the stream, if the fish are going that way and your normal vector is pointing that way, then you get no fish, because it doesn't matter how many are swimming past, that's this quantity. In this case, the two vectors are perpendicular, so you're getting an angle of 90 degrees in there. The cosine of that angle is 0, so you're not getting any fish that are actually being caught by the net. So this is the quantity that I would like to take advantage of. I'm going to let little f be this product where theta is the angle between the vector field f and the normal vector to the surface. So this will tell me actually, like, if this is, well, if the flow is of fish swimming through the water, then you would measure this kind of a flow. The magnitude of this flow would be measured in things like fish per square centimeter per minute. Of course, it has a direction as well, but you're counting how many fish swim past every square centimeter in a minute. You'll take that quantity and reduce it by this. This has no units. This is a pure number. So this is still a number of fish per square centimeter per minute. If you multiply that by the number of square centimeters of your net, obviously a bigger net gives you more fish, then you multiply the value of this function times an area, and you'll find out how many fish you are catching per minute in total, at least across your little portion of a net. If you add that up portion by portion on your net, then you'll get the number of fish per minute here, plus here, plus here, plus here. And so the integral of f with respect to area, that is going to capture the idea of just how many fish are we catching per minute, or how many gallons of water are passing through the opening of our drainage pipe every minute. So this is a numerical quantity that you would want to multiply by an area and then add up section by section. So computing this integral turns out to feel very natural from the perspective of the people who are doing the applications, the scientists and engineers. And given the way that I'm calculating this function little f, it seems perfectly natural to write it as a dot product of f with a vector that's normal to the surface, a unit normal vector. I mean, this dot product can be computed exactly like this. It's the magnitude of the first vector times the cosine of the angle between them times the magnitude of the second vector, which doesn't appear over here. So you need that second vector to be a unit vector, so its magnitude is 1. So people will very often write literally this. They'll say that I would like you to compute a surface integral over this surface where the function that you're integrating is capital F dotted with n, and it's understood that n is supposed to be a unit normal vector to the surface at each point. That unit vector can change as you move from point to point. And they may put in something like dA here on the side to just remind you that you'll be multiplying the values of that times the areas of the little pieces of your surface. Okay, so this is all about surfaces, but you know, it kind of follows the same flow as everything that we've been doing, that we did previously for curves. It's not the mathematicians, but the applications people who come in and say, you know, I might want to look at, compute the integral of a function that's calculated by taking the dot product of a vector field with some unit vector. They give you good reasons for that. And then after they've explained that that's something they might want to do, then we as mathematicians can start to jump in and say, oh, look, you're just computing the values of some scalar valued function now. These are just numbers, not vectors. And you're, you know, doing the usual thing. You're multiplying them by the size of the piece and adding them up. And that will give you some number. Now, that's the general concept of what these new surface integrals might be. They're related to the old surface integrals. I mean, they are just examples of the old surface integrals, but they arise from a vector field. And we use a notation for them that says something about that vector field. That makes people happy to have a notation that reflects the origin of the problem. As far as calculating these, how do you calculate this number? Well, we've already indicated a method for computing surface integrals, so that's exactly what we would do. So,
Sorry to interrupt.
Yes, please do.
I just wanted to ask, what did you say the vector n represented again?
N is a unit vector that will be normal to the surface. It'll represent a perpendicular direction to the surface, right? So I needed something that will capture this cosine for me. This cosine factor says how much of the flow is reduced by virtue of where my surface points. When your surface is pointing, is kind of face on into the flow of the force, then you feel like you're capturing 100% of the magnitude of your force. But when there's an angle in there, then you're getting less and less of that force until you actually get none of it when the surface is sort of facing, sorry, it's not facing the force, but it's kind of running parallel to the force. It's a little tricky to describe because, you know, the direction of the force at each point is a single arrow. I only need one finger to indicate where the force is going. But my surface, it takes the whole palm of my hand. So how do I express the sort of the combination of the orientations between those two? And the easiest way to do it is to replace the whole sense of the direction of the palm of my hand by just taking one vector that's perpendicular to that. And then asking about, gee, how is the flow of the force related to the orientation, the direction of this surface? That's really the same as saying, how do those two vectors compare in their directions? And the comparison of the directions is computed by means of a dot product. So again, I'm glad you asked. This little n stands for a unit vector that is normal, hence the n. It's normal or perpendicular to the surface at each point in the surface. And I'm going to need that in a minute as I actually try to start grinding out the calculations. I mean, how did I compute the line integral before, the path integral rather? Well, you know, you need to write down the function that you're integrating, which in our case over here was a dot product. And then you'll need to multiply that. Here, didn't I do it? You need to write down the function that you're integrating and multiply that by this fudge factor that says that there's a difference between the lengths on the curve and the lengths in the parameter space. And we'll have exactly the same situation here. I mean, as I try to compute this surface integral, well, you know, the way you compute any surface integral is you begin by finding a parameterization. I've been using the letter capital T to be my parameterization of a surface. So let me say that. Use a function T that goes from the plane into three-dimensional space as a parameterization. And then you know the drill. When you want to compute the integral, a surface integral over a patch of space, you have to rewrite three things. You change your surface, your region of integration, to now be a portion of the UV plane. I get a set D that's contained in the UV plane. You have to change your integrand, so you take the composite with capital T, you substitute in your parameterization that gives X, Y, and Z as functions of U and V. You shove that into the function that you're trying to evaluate. And then as far as the area elements, you want the areas of the patches of three-dimensional space that's not quite the same as the areas down in the two-dimensional space, because you know there is this fudge factor. And all right, that's how you compute any surface integral. In our particular case, this little f has been defined to be this dot product of a vector field that's defined on three-dimensional space and this unit vector thing. So I'll write that much out. Let's see, this f composed with f means I'll take the vector field capital F and compose that with capital T. Again, all that means is you look at your vector field that spits out a vector at each point x, y, z. It's calculated in terms of the x, y, and z, but the x, y, and z coordinates will be calculated from u and v, just as is always done in a parameterization. So that's the capital F part, and then you need to multiply by a unit normal vector. So that replaces this. And the rest of this, I'm just going to have to leave it unchanged. There's the fudge factor for what they call the area element, and that's what you'll have to integrate. Now, at some point, you got to address the question of how the heck am I going to create a unit vector that's normal to a surface? And the answer is, you've already been doing it and you didn't even think about it. You see, the whole reason that all of this stuff came into our life was that TU and TV were, at each point on the surface, they were calculating two little tangent vectors. And those two tangent vectors together sort of generated a parallelogram that was a portion of this surface. Previously, I only wanted the area of that parallelogram, and the area of that parallelogram is the magnitude of this cross product. But that cross product, it's a vector. Yeah, it's got a magnitude, and that magnitude is the area that we were interested in before. But that cross product also has a direction. You may recall the direction of a cross product is it's always perpendicular to the two vectors that you're taking the cross product of. And both of those vectors were tangent to the surface. So this guy is going to be a vector that's perpendicular to both tangent vectors, which means it's perpendicular to the whole tangent plane. And so it is a normal vector. So when you want to get this unit normal vector over here, the most natural thing in the world to use would be to take the vector TU cross TV and say, hey, that is a vector that's normal, perpendicular to the surface. It's not a unit vector though, so you do have to divide by the length of that to get it into a unit vector. And now I can put that into this expression. I don't have to change very much. You'll take F composed with T, that's the vector field. You take the dot product with, well, this whole mess. So I'll take TU cross TV, and then, well, I can divide by the magnitude TU cross TV at the end instead of dividing before you take the dot product. You can divide by this number after you take the dot product. So that is just a rewriting of that. But now I have to multiply by the rest of this integrand, and look at what happens. I called it magic in the curve setting, and it's happening again now. You get a cancellation of the two messiest factors that show up in this calculation. I don't know what else to say except magic happens. Okay, it's not really magic. There's some mathematics that makes this reasonable. But as far as you're concerned, what this is going to mean is that as you compute these particular types of surface integrals, the ones that come from a vector field, you're actually off the hook. You don't have to compute the magnitudes of TU cross TV. You still do have to compute TU cross TV, but not the magnitudes. So this is all you're left with, is that your surface integral is now computed as the integral over whatever portion of the UV plane that you need to parameterize things. And what you're going to integrate with respect to du dv will be the following number. You shove your parameterization for x, y, and z into the vector field, and you take the dot product of that with this cross product, tu cross tv. And that'll be a function of u and v, of course. We've turned this into a function of u and v. This will be a vector, and that'll also be a vector. Compute the dot product of those two vectors, and now you'll have a number. It's a number computed from u and v. So this is an ordinary function of u and v, and you just have to integrate it with respect to u and v across the subset of the uv plane. So I did it for line integrals, and now I've done it for surface integrals. For surface integrals, we've just discussed quite a few things. One of them is, I do want you to understand the meaning of what they are, and this is where I'm focused on the idea of the fish going by. I'll give you another application in a second. You do have to get used to the notation, and you know, you do sometimes see people writing things in this form, p dx dy plus q dy dz, and so on. I'm not going to use that notation because there's actually some ambiguities in there. Turns out there's plus or minus signs that will confuse you, and so I'm not going to use that notation, but I might use this notation a lot. So this would be the notation that captures all the sense of what it is that I want you to compute in the first place. And that notation is tied to the meaning that underlies this. Then the other thing that you need to get used to is how to compute these things. And that's what's captured here at the top of this page. You need to begin by finding a parameterization. Sorry, there's no way to avoid that. And you'll do some substitutions, and you will have to go through the cross product, but at least you don't have to compute any magnitudes of that cross product. Instead, you'll compute a dot product. And then finally, in addition to all of these, there's one other topic this will be the content of Chapter 8, is that there will be some theorems, and so I haven't done those with you yet. But all these other three, I have tried to introduce you to surface integrals from these three different perspectives. There's the meaning, there's the computation, and just to get used to the notation. So I gave you some interpretations of these, this kind of surface integral in terms of catching fish or drawing water out of a river. There are other, historically, the first ones had to do with when the vector field indicated lines of electromagnetic flux. So you feel an electric field or a magnetic field, and you've put some sort of metallic surface in the way of it, and you're going to look to see what is the induced electric field, the electric flow within that plate of metal or something. Or you imagine that you're walking around on an asteroid, and you feel these lines of a magnetic flux coming out, and so you think, oh, well, there must be some sort of magnet that's hidden inside. And in order to get a sense of what's inside this, we actually just walk around on the surface of our asteroid with a little metal detector, which has a plate at the end, and you kind of got to orient the plate along the surface to capture the flow that's coming out. So you see, once again, there's a vector field already in place, and you're walking along on the surface, but the direction of the surface compared to the direction of the flow, that's what's somehow relevant in this. You would make, if you saw the electric lines of flux coming out on this side, you figure that there's something inside, until maybe you have a similar situation and you walk around and you see these lines pointing that way, and then on the other side, you feel like the lines of flow are going opposite. In that case, you realize, oh no, there's nothing inside my asteroid. Anything that I'm sensing with my metal detector, it comes from some other object that's far away, and it's just kind of, you know, producing a magnetic field that I'm accidentally in the way of. So, yeah, go ahead, Nathan.
This is just a little side question, but are you saying that in this application, asteroids are actually propelled by a gravitational flux from like other objects out in the solar system?
Well, I mean, sure. Suppose that you were on you stumbled on an asteroid and you kind of, you know, your spacecraft landed there and you got out and you started to walk around and you say, my gosh, I feel very heavy on this asteroid. It must be incredibly massive. Well, that is an explanation. If you felt a very strong gravitational field, the lines of gravitational force pulling you inwards. Okay, great. But then you might notice, oh, I'm sorry, I just merely landed on an asteroid that happens to be very close to the sun. And so the force of gravity that I'm feeling that's so strong on this side of the asteroid, it's only because the sun is on the other side where I can't see it. If you had walked around to the opposite side of the asteroid, those two situations would now feel very different. In the case where you happen to have a very massive asteroid, when you get over to this side, you will still feel yourself being pulled inwards. Whereas if it's basically a hollow asteroid that's near the sun, well, when you stand on this other side, you'd say to yourself, wow, I feel like I'm actually being lifted off the surface of the asteroid, because the real source of the gravitational field in this case was the sun. So in both cases, you can actually do one of these surface integrals. The surface would be the surface of the asteroid. The vector field you're measuring, both its magnitude and its direction, those would be the lines of the gravitational force. But there's going to be something different in the two circumstances. Even though the force field feels identical on this side of the asteroid, on the far side of the asteroid, the vector fields they've been replaced by their negatives. And I'll just clue you guys in, when it comes to the theorems, what we're going to discover is that this kind of thing actually works, that you can tell what's inside the asteroid. Now that would ordinarily be measured by a triple integral. You'll be measuring, to get the mass of this, you would multiply the density, the old-fashioned grams per cubic centimeter density, by the volume of the asteroid. So you would have to do a triple integral to figure that out. As it turns out, we will be able to figure out the mass of the asteroid by walking around only on the surface of it and computing a surface integral where we measure the gravitational field at each point on the surface, and we add together the contributions at every spot along the surface. So that will be telling us that a certain kind of surface integral will match a certain kind of three-dimensional integral. That's one of the theorems that we're going to see in Chapter 8. It's actually very cool, and historically, that was the kind of thing that motivated all these discussions of these funny kinds of surface integrals and the funny kind of line integrals to boot. So I'm getting ahead of myself. There will be great theorems, really cool theorems, but at the present time, I just want you to feel that you understand what you are computing and that you know how to compute it. That'll suffice for today. Well, it has to suffice because I've already gone 4 minutes over. All right, any other last minute questions you want to throw at me on this material? We're hitting some big stuff now. It's hard. The computations are hard, but the ideas are actually not all that complicated. They should feel fun, especially once you start walking around. Sorry about the camera. I don't know why it's flickering. All right, guys, I'm going to cut it off now. I have to finish grading your exams. I do have to get your homework up. And I'm open to your feedback on how this last exam went. When it comes to the final exam, I guess I'm going to structure it pretty similarly, but I'm starting to figure out some things I'm going to change a little bit to make it better. Okay, so stick with me in office hours if you want. Otherwise, I'll see you on Wednesday.